Hello and good day again everybody. Welcome again to Engineering Physics, and for today's video, we would now be discussing about torque. So torque is often referred to as moment of a force or simply moment, and it is to be represented by the Greek letter tau. So this Greek letter tau right here looks like a letter T because, well, it is letter T in their country. However, this is once again the Greek letter tau. Okay, so as per defined here, so torque is to be defined as the measure of the effectiveness of the force in producing rotation about an axis. So suppose that we would be having a stick, and let's say that in this stick, this particular point is now to be a fixed point. So what that means is that no translational motion is to be present here. And in Filipino, hindi dapat gagalaw sa horizontal and vertical axis itong point na to. So that is once again to be in Tagalog. Okay, so let's say that once again this is now to be a stick with a fixed point, and let's say that we will be applying a force perpendicular to this stick, and let's say that this is now to be our force F. So let's say that this is now to be our force F. So if force F is present here and that this part here is now to be a fixed point, the tendency of this stick is to rotate in this manner because of course a force is to be present at this point. However, let's pretend that the force is now to be acting here. So if this is now to be the force, the tendency of this stick is once again to move at this particular motion. Okay, so that is for torque. And torque, so torque is to be equal to force times the lever arm. So your force is, well, basically this force, and the lever arm is to be the perpendicular distance from your fixed point or from the point that you are analyzing, and in this case, we are analyzing this point, up until your force. So once again, this should be the perpendicular distance. So perpendicular. Okay, so in this case, so as I have said earlier that your force F is to be perpendicular with this stick, it means that your lever arm L is now to be equal to this particular distance. So this is now to be L. So for you to get the torque present here, just multiply force and your lever arm. Okay, so what if, for example, that let's say your force is not to be directed perpendicular to this stick. So for pretend that your force is now to be located like this. And as you can see, this is not 90 degrees. So this is not 90 degrees. And thus, this is not perpendicular. So in this case, you cannot just multiply force by this particular length here because once again they are not perpendicular. So what you are going to do is that you will now be projecting this downwards. So you will now be projecting this, and you will now find a point here that is, that will make it perpendicular. So in this line that I have drawn, so you will now be searching for that particular position wherein those two lines would be perpendicular. And in this case, this is now to be the perpendicular line. So if this is now to be 90 degrees, so this is now to be your lever arm. Okay, so moving forward, so once again, this is now to be for torque. So let's say that this force F is now to be 10 newtons. And let's say that the length of this lever arm here is now to be equal to 10 meters. So for torque, that is basically 10 newtons times 10 meters. So with such, without using our calculator, this is basically 100 Newton meters. So this is now to be the unit for torque. But take note, guys, that in our previous video for work, so work is also equal to force times displacement, and if you would be getting their units, this is also to be in terms of Newton meter. And this Newton meter is actually equal to joules. However, in moment, this is not equivalent to joules because this force and this lever arm are to be two perpendicular entities. And for work, your force here and your distance here are two parallel entities. So there, and with that, we cannot convert Newton meter here into joules. So there. And also guys, common misconception is that moment is to be synonymous with momentum. But once again, that is just a misconception. Moment and momentum are two different entities and two different quantities. So with such, we cannot equate moment and momentum. So once again, both of them are two different quantities. Okay, so moving forward, there is also this thing which we call static equilibrium that we have already discussed in the previous videos. So in static equilibrium, so as per defined before, the summation of forces is to be equal to 0, because if the summation of forces is now to be equal to mass times acceleration, and if acceleration is to be equal to 0, it is now to be in static condition, thus summation of forces is equal to 0. And it is said here that the net force on a particle is 0. So ito yun guys. Okay, so as seen here, so there is no translational motion or rotational motion. So for translational motion, this is basically the motion along the x and y axis. Thus, the summation of forces along the x-axis equal to 0. The summation of forces along the y-axis is equal to 0. And if there is to be a z-axis, the summation of forces along the z-axis is also equal to 0. So that is for translational equilibrium. So for rotational equilibrium, so the summation of moment or the summation of torque, that should be equal to 0. So what this means is that if you would be adding all the torque present in one entity, we can say that it is under static equilibrium if their total is to be equal to 0. So once again, in the previous meeting about dynamics, we have already discussed about this before. Okay, anyway. So proceeding here, so let us have this as an example. Okay, so I have said earlier that the summation of moment should be equal to 0 or the summation of torque. And in this case, if let's say that this is now to be a fulcrum and this is now to be a fixed point, so it means that if we would be getting the moment about this point, the sum should be equal to 0. So let us prove this. So summation of moment once again is to be equal to 0, and I will be assuming that all moments going to the clockwise direction are to be positive. So once again, in using Fourier sign convention, it would be up to you if you want it to be clockwise positive or counterclockwise positive. So whatever your sign convention is, you would still be arriving at the same answer as long as you know, of course, your sign convention. But once again, I want my sign convention to be clockwise positive. Okay, for your torque or moment, this is now to be equal to force times lever arm. And if this is now to be the point that we are analyzing, so I would be getting the moment here for me not to include the support reaction here. So ulitin ko lang, dito tayo magmo-moment sa part na to. And for this force here, so for this 2 Newton force here, so its torque or its moment is to be 2 Newtons times lever arm. And the lever arm here is to be measured from this location up until, of course, this. So as you can see, the lever arm here is to be the perpendicular distance from this point up until the force. So thus, this is now to be 5 meters. So 2 Newtons times 5 meters. So my sign convention would be clockwise positive. So what is now to be the rotation of this 2 Newton in reference with this point? So if this is now to be your stick or the beam, and if I am to apply this 2 Newton force here, the tendency of this stick is to rotate in this particular motion. So once again, as brought about by this force, its rotation would be like this, which is counterclockwise. So if it is counterclockwise, it means that this is now to be negative because once again, my sign convention is counterclockwise positive. So there. And as for this force here, so 4 newtons times, so let's pretend that this is now to be located at the midspan. So suppose that this is now to be located at the midspan. So its lever arm would be 5 meters divided by 2. Thus, this is now to be 2.5 meters. And if this force is to be applied, and so if this is now to be the point and this is not to be our stick, our imaginary stick, and if we would be applying a force 4 newtons, its tendency is to rotate in this manner. And this is now to be a clockwise direction. Thus, it would now be positive, since once again, my sign convention is to be clockwise positive. So positive, force times lever arm, so our force is to be 4 newtons times lever arm of, so 5 meters divided by 2. So I am assuming that this 4 newtons here is to be located at the midspan of this particular span. Thus, this is now to be 2.5 meters. So 4 newtons times 2.5 meters. So let us check if this is now to be equal to 0. So negative 2 times 5 plus 4 times 2.5. So my answer here is now to be equal to 0. Thus, this system, so system is under equilibrium. So if your answer is not 0, it means that the system is not under equilibrium. So it would be as simple as that. Okay, so let us have another example. So in this example, we would now be determining the force F required for the system not to rotate at point A. So if this is now to be point A, so we will be getting the moment here, and we will now be searching for force F for this particular system not to rotate. So for it not to rotate, the summation of moments about A should be equal to 0. So with that, I will now be getting the torque of all of these forces, and I will now be equating it to 0. Okay, so for the first one, so for this 2 Newton force, so once again, torque is equal to force times lever arm. So for this force, if this is now to be our reference point, so by the way, my sign convention would be, so maybe this time I would be using counterclockwise positive. As to why? Because, well, I just like counterclockwise positive. Okay, so with that, so 2 newtons, so this is for the first force, so 2 newtons times, so what is to be the lever arm from A up until 2 newtons, so they are to be exactly, 2 newtons is to be located exactly at point A, thus this is now to be 0 meters. So this is now to be for the 2 Newton force. So about for the 4 Newton force, or let's say I would be getting the torque of this force F first. So if this force has the tendency to rotate point A in a counterclockwise direction, so this is now to be positive. So this is now to be positive because my sign convention once again is to be counterclockwise positive. So thus, positive force F, so I do not know what force F is yet, times the lever arm of 5 meters. So 5 meters. Okay, so there. So that is for force F. So once again, it is positive because the tendency of force F is to rotate point A in a counterclockwise direction. And my sign convention once again is to be counterclockwise positive. What about for 4 newtons? So if this is once again your point F, so the tendency of the 4 Newton force is to rotate point A in a clockwise direction. Thus, this should be negative. So negative 4 newtons. So force times lever arm. So what is now to be the lever arm here? So if this is now to be 2.5 meters, so the distance from point A up until the 4 Newton force is to be equal to 5 meters plus 2.5. Thus, 7.5. So this is now to be 7.5 meters. So there are no more forces. So I would now be equating this to 0. So simplifying this equation, this would just simply cancel out. And F times 5 meters, so this would now be equal to 5 meters F minus So 4 times 7.5. So looking at the calculator to your left, 4 times 7.5. So this is now to be equal to 30. So 30 Newton meter. So this is now to be equal to 0. So transposing 30. So 5 meters F is equal to 30 Newton meter. So if I am to divide both sides by 5, just for me to arrive at an answer in terms of force. So the answer here, so meters would now cancel out. So F is now to be equal to, so 30 divided by 5, so 6 Newton. So this is now to be equal to 6 Newton. So final answer. So this system must have a force F located here for the system not to rotate at this particular point. So there. Okay, so another important aspect in our topic is to be the term center of gravity. So in solving for torque, center of gravity is one important thing to consider. So the center of gravity of an object is the point at which the entire weight of the object may be considered concentrated. So if you have already seen one of this in your lifetime, ibig sabihin nun, matatanda na kayo, pwede na kayo mag-asawa. Kidding. Okay, so in this particular mass here, so of course in this bird, this part of the wings is to be subject to gravity, thus it would be having its weight, as well as for this wing, as well as for its body, and as for its tail. But we can say that the center of gravity of this particular bird is to be located at this particular point. So let's say that the wing is to be, let's say, 100 grams, or what is to be 100 grams in newtons, 0.1 times 9.81. So this is now to be, let's say, 0.981. So let's say that this is now to be 0.981 newtons, as well as for this, so 0.981 newtons. And let's say that this is also 0.981 newtons. So if we would now be getting the total weight of all of the entities, so its total weight is now to be equal to 2.943 newtons. And if the center of gravity is to be located at the beak, it means that the entirety, so we can assume that the entirety of the weight is now to be concentrated at this particular point. So that is to be our assumption. So 2.943 newtons. And in this stick, so I am pretty sure that you have already discussed this in your laboratory classes, wherein you have balanced a stick. So if let's say that this stick is to be balanced in this particular location, it means that its center of gravity is to be located here. And thus, the entirety of the weight of the stick is to be concentrated at this particular point. Thus, that is why this meter stick is balanced here. Okay, so if you want to search for the center of gravity of a certain object without computing, what you will be doing is that you will be finding a point in that particular object in such a way that if you will be placing your finger onto it, that object would balance. So for pretend that you would be having a certain laptop, for pretend that this is to be a laptop, well actually it is a laptop. So if I want to search for the center of gravity of this particular laptop, what I am going to do is that I will be finding a certain point in this laptop in such a way that if I am to place my finger onto it, the laptop would balance. So parang ganito siya. Pero syempre hindi ko gagawin. At isa na nga lang yung kidney ko dahil sa laptop na to. Joke. Kidding. Okay. So let's pretend that I have this book. So in this book, so if I want to search for its center of gravity, what I am going to do is that I will be searching a point in this book in such a way that if I am to place my finger onto it, the book would balance. Hindi ko mahanap. Huwag na lang. Okay, basta ganun yun. Okay, so proceeding, let us just have an illustrative example wherein center of gravity is now to be used. Okay, in this problem, kunwari wala kayong nakita, Pangit ng drawing. Okay, so redrawing the problem. Okay, so an object is hung at the end of the stick as shown. So wala pang nakalagay, mag-drawing muna tayo. So I will be drawing an object here. So for pretend that this is now to be the object. And it weighs 5 kilograms. I mean, it has a mass of 5 kg. So 5 kg. So we will now be determining the torque in Newton meter at the support. So this is now to be the support. So the weight of the stick is 1 kilogram and the center of gravity is located at the center of the stick. So if this is now to be the entirety of the stick, so this stick is to be, has a length of 0.25 meters plus 0.75. And if I'm not mistaken, that is to be 1 meter. So with such, 1 meter. So it is said here in the problem that the weight of the stick, 1 kilogram, is to be located at the center of the stick. So if the center of the stick is to be here, so this is now to be 0.5 and this is also 0.5. Thus, if we would be measuring 0.5 from this point up until this point, this is now to be the centroid as well as for this part. So this is now to be 0.25 meters. This also 0.25 and this is now to be 0.5 meters. Okay, if its center of gravity is to be located at this part, so it means that the entirety of the weight is to be concentrated here. So this is now to be 1 kilogram. Okay, so the first thing that we will be doing here is that we will be drawing the free body diagram of this. So if this is now to be the stick, since we have a support here, there is to be a vertical force here. So this is now to be for the support. Which is to be a vertical force. And as for this, so there is to be a weight here. And if this is now to be 1 kilogram, so if I am to multiply 9.81 meters per second squared, this would now be equal to 9.81 newtons. So in other words, this is to be 9.81 newtons. Okay, so proceeding. So for the 5 kilogram force here, so there is also a weight that is to be applied here. So it would be up to you if you want to place it here or if you want to be placed at the top. So it really doesn't matter. So in this case, so the weight of this object is to be, so 5 kilograms times acceleration due to gravity. That is now to be equal to 49.05 newtons. Okay, so as for this force F here, or let's say that this is now to be the support reaction. So let's say that this is now to be R. So we can solve for it. However, there is no sense of solving for it because if we are to get the moment about this location, the lever arm of this reaction R is to be equal to 0. So it really doesn't matter. Okay, so with such, since we are now to determine the torque in Newton meter, so we would now be getting the summation of moment about point B. So if this is now to be point B, so summation moment B. So let's say that it is now to be clockwise positive. So once again, it would be up to you if you want clockwise positive or counterclockwise positive. So considering this point, so for your support reaction R, you would just be multiplying it by 0 because its lever arm is to be 0 meters. Thus, 0. Okay, and as for this 9.81 force, so rewriting all the dimensions here. So from this point up until this point, so this is now to be equal to 0.25. So it is to be this. And this is now to be 0.5. It is now to be this. Okay, so for the 9.81 force, so since this force has a tendency of rotating point B in a counterclockwise direction, it means that this is now to be positive. So positive 9.81 times 0.25. 5. So that is for this particular force. And what about for this force? So as you can see, it is also located. I mean, it is also directed downwards, and thus its tendency is to rotate point B in a clockwise direction. Thus, it is also positive. So positive 49.05 newtons times the lever arm, and the lever arm is not 0.5. It is to be measured from this point up until this point. So in other words, it is 0.25 plus 0.5, thus 0.75 meters. So this is basically the summation of moment at B. So with that, the summation of moment at B is equal to the torque at B, and this is now to be equal to 9.81 times 0.25 plus 49.05 times 0.75. And our answer here is now to be equal to 39.24 Newton meter. So this is now to be our final answer in this particular problem. Okay, so another example. So 3 masses are attached to a uniform meter stick as shown. So this is now to be our figure here. So the mass of the meter stick is 150 grams, and the masses are to the left of the fulcrum. I mean, the masses to the left of the fulcrum are 50 grams and 75 grams respectively. So find the mass of the third mass that balances the system when attached to the right end of the stick. So basically, this is now to be M3, and this M3 is actually the mass that we are searching for. Okay, so the first thing that I will be doing here is that I will be drawing the free body diagram. So when I am to draw the free body diagram, so we will now be converting all of them into forces. So if this is now to be the meter stick, so suppose that this is now to be the meter stick, so mass 1 is to be attached at the left end. So with that, let's say that this is now to be mass 1. So mass 1 is to be equal to 50 grams. So 50 grams. And mass 2 is to be located here. So it is here. So this is now to be mass number 2. So for mass 2, this is now to be 75 grams. And since we have a support reaction here, a support here, it means that we would be having a certain vertical point here. An upward force here. So this is now for the support. And as for the support, we don't know what that is. So let us just type R here. Write R. So this is now to be the reaction at the support. And for your mass 3, so this is now for mass 3. So the weight for the mass 3 is actually unknown. Okay, so as said here, that the stick is said to be 150 grams. So for the stick, and if the stick is now to be 150 grams, so of course we would now be applying another force here at this particular portion, and this is now to be 150 grams. So is the center of gravity given? So it is not. So if the center of gravity is not given, by default, it should act at the center of the stick itself. So if the stick is to be measured as 30, 40, 30, so 30, 40, 30, so this is basically 100 cm. So if this is now to be 100 cm, this should be 50 cm, and this should be 50 cm as well. Okay, so rewriting. So this is now to be 50 cm. So 50 centimeters. Then this is also 50 centimeters. Okay, and as for this distance, so this is now to be for a moment. So this is once again 30 centimeters. And if this is now to be 40, this is now to be 20 centimeters. This is also 20 cm. And this is to be 30 cm. So if I would be getting the total of all of them, so 30 plus 20, 30 plus 20 plus 20 plus 30. So this is now to be 100 cm already. So if it is said here that this system is balanced, if you would be getting the moment about any point, it should be equal to 0. So if you would be getting the moment at this portion, at this part, at this part, this part, or anywhere, the moment should be equal to 0. So it will be up to us on choosing the location of where we would be getting the moment. And in our case, it is better if you would be getting the moment at this position for the lever arm of R to be equal to 0, and thus we do not need to solve for R any longer since we are only concerned with the value of M3 and not R. Okay, so the traditional approach here is for us to convert them. So we would be converting them first into Newton. So that is now to be the traditional way. But you can skip with that part as long as you know the units. Okay, so with that, so what I mean here is that if you would be getting the summation of moment about, so let's say that this is now to be point S for pretend. So if you would be getting the summation of moment about the S point, this should be equal to 0 because it is said here that the system is to be balanced. And for our sign convention, maybe I want it to be clockwise positive. So there. Okay, so once again, we would be getting the moment about this particular point. Okay, so for the first force here, so once again, I can convert it first to newtons and I can convert cm into meters first for us to arrive at an answer in Newton meter. But since we are solving for M3 in terms of grams, I would skip with that part and I will be making use of these units here as long as I will be consistent with my units. So if this method confuses you, once again, it is better for you to convert them first into newtons and convert them first into meters. So our answer should be the same. Okay, anyway, so as for this first force here, so 50 grams. So 50 grams times what is now to be the lever arm. So by the way, guys, moment is equal to force times lever arm. And for our lever arm here, it should be the distance from this point up until the end. So with that, as in here, 40 plus 30. So this is basically 70 centimeters. However, so what is our now to be our sign convention here? So for our sign convention here, if this is now to be our point, and if this is now to be the force, the tendency of the force is to rotate point S there in a counterclockwise direction. Thus, this should be negative because once again, my sign convention is to be clockwise positive. Okay, so for example that you want it to be counterclockwise positive, so it's just that your sign convention would now be reversed, but your answer should be the same. So your answer should exactly be the same. Anyway, so proceeding, so as for 75 grams here, the tendency of this force is to rotate point S in a counterclockwise direction. Thus, it is once again negative. So negative 75 grams. Negative 75 grams times our lever arm and our lever arm here. So from this point up until this point, that is now to be 40 cm. Okay, so I will just be moving it here. Okay, so proceeding. So we also have this weight 150 grams. So as you can see, the tendency of this weight is to rotate point S in a counterclockwise direction once again. Thus, this is once again negative. So negative 150 grams times what is now to be the lever arm. So if as you can see here, if this is now to be our point and this is now to be 20 cm, so thus 20 cm. For your R, so for R, its lever arm is to be 0 cm. Thus, it would just basically be equal to 0 and I would not be including it here any longer. Okay, so for M3, so last but not the least, so M3, so if this is now to be our point and this is now to be M3, the tendency of M3 is to rotate point S in a clockwise direction. Thus, this is now to be positive. So with that, positive, so M3 times our lever arm of 30 cm. So it would be from this point up until this point. So 30 centimeters. So I'm sorry if you if you cannot see. So I would just be moving all of this to the left. Okay, so here I would just be moving the entire board. So apologies. So there. And since the summation should be equal to 0, so this is now to be equal to 0. So one equation, one unknown. So simplifying this, so if I am to combine all of this, so this is now to be negative 50 times 70 minus 75 times 40 minus 150 times 20. So this is to be equal to negative 9,500 gram cm. So as you can see with the units, it is not Newton meter as per described earlier, that is to be the default unit for our moment. So this is because I did not convert. Okay, so this is to be plus m3 times 30 cm. So this is to be equal to 0. So transposing this to the other side. So mg, m3. So saan nanggaling yung g? So this should be m3. I'm sorry. So m3 grams. So m3 times 30 cm is equal to 9,500 gram cm. So if I am to divide both sides by 30 cm for me to get rid of this 30 cm, so m3 is now to be equal to, so 9,500 divided by 30, and our answer here is now to be equal to 316.66 grams. So as you can see, centimeters would now cancel out, and thus we would be arriving at a unit in terms of grams. So for the system, so for this particular system not to rotate, M3 should have a mass of 316.66 grams. So once again, if you have converted this into newtons and converted this into meters, so your final answer here, so for the weight in 3, that should be equal to 3106.5. However, if you would be converting it into grams, it would become 316.667 grams. So that's it for this particular problem. Okay, so let's have another sample problem. So in this problem, the given plate is fixed at point O and is allowed to rotate at this point. So we would now be finding the total torque applied by the forces. So if this is now to be our point O and it is now to be rotating at this particular point, so we would now be finding the torque. So for us to get the torque, at point O, so this is basically the summation of moments about point O. And this is not equal to 0, I think, because it is not said in the problem that it is under equilibrium. So once again, I only think that it is not equal to 0 because of course we may solve it as to be equal to 0. So let us find out if it is to be in equilibrium or not. Okay, so with that, my sign convention, so let's say that I want it once again to be clockwise positive. So with that, if this is now to be our point O, so for this particular force, so if this is to be our point O and this is now to be the force that we are considering, the tendency of the 4 Newton force is to rotate point O in a counterclockwise direction. Thus, this should be negative. So negative. So once again, torque is to be equal to moment and it is also equal to force times lever arm. So our lever arm here is to be 2 meters. So 4 newtons times 2 meters. So there. Okay, what about for this 6 meter force here? So 6 meters is to be located at this point. So as you can see, it's perpendicular distance. So once again, perpendicular distance and not a parallel distance. So its parallel distance is to be 4, but its perpendicular distance is to be equal to 0. So plus 6 newtons times 0 meters. So once again, for your lever arm, it should be perpendicular. So if you can see here, this is now to be perpendicular with this. However, they do not have any perpendicular distance. So there. Okay, and as for this 5 Newton force, so if this is now to be the force, so its perpendicular distance is to be measured from this point up until this point, because this is now to be the line of the force. So if this is now to be the perpendicular distance, this is now to be 5 newtons times 4 meters. So by the way, if this is now to be the line, so the tendency of this 5 Newton force is to rotate point O in a counterclockwise direction. I mean clockwise direction, I should say. So clockwise direction, thus this should be positive. So this is now once again to be plus. So plus 5 newtons times once again perpendicular distance, and you wouldn't be solving for distance for this distance any longer because this is not to be the perpendicular distance. The perpendicular distance from point O up until the 5 Newton force is to be this. So from this point up until this point, because your force here is to be, this is now to be its line of action. Okay, so times 4 meters. So okay, so solving for this, so this is now to be equal to, so looking at the calculator to your left, so negative 4 times 2 plus 6 times 0 plus 5 times 4. So our answer here is to be 12 Newton meter. So this is now to be our final answer. And since it is positive, its direction is to be clockwise. So there.